That dot that we saw right there in the center is called the center of the circle. And what's true about the circle is that everywhere you go, there's a radius. So here it is. For your notes. A circle is the set of points in the plane equidistant from a center. That's it. A set of points in the plane equidistant from the center.
And how many points are there?
There are definitely an infinite number of points. Congratulations. Yes. In fact, I'll go even further and say there's an uncountably infinite number of points as opposed to a countably infinite number of points. So it turns out that the word countable in math is kind of a funny word. Countable specifically refers to the counting numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, out to infinity. So if you have a set of things that can be counted in that way, you call it countable infinity. And anything that is not such, like the number of points in a circle, is uncountable. That's bigger infinity than the countable infinity.
So countable infinite would be a QP of 1, 2, 3, 4, like.
Yes. Yep.
So pi would be which
So pi is just a single number.
yeah, but with all the numbers going up,
Because you can start counting them, 3.1, 4, 1, 5, 9, 2, 6, 5, 3, 5, 8, 7, 9.
oh, thank you.
Yep. Okay. All right, now where are we going with this? So what we're going to do is we're going to consider, first of all, an object moving along a straight line. Maybe the object does this, and it doubles back on itself, and it does that, and it does that kind of thing. And what I wanted to do was to have you see where the object is speeding up and slowing down, but it's not. My question for you, if the object is moving like this, where at least do we see acceleration taking place? Yeah.
The bends where it turns back and goes back forward.
Okay, and form.
Because acceleration is a change in velocity, and velocity involves direction.
That's it. As soon as we change direction, we've necessarily changed our velocity, even if we didn't change our speed. Now, as it turns out, if I'm moving in a straight line, if I want to change the direction, I have to change my speed too, because I actually have to slow down and stop before I can turn around. So there would be both a change in speed and a change in direction, right around here, 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 and here. Now I want to consider moving in a circle for just a minute. And today we're going to limit ourselves to uniform circular motion, which does not mean that you put on a uniform and move in a circle. But it means instead, uniform circular motion means that we have constant speed moving in a circle. So the classic example here would be that I've got a car, here's my car, and my car is going to move around the circle here, and I'll line it up. Now, how come I had to line it up? Why was it not reasonable for my car to be pointed this way instead of that way? What does the car have to do physically in order to go around this circle?
Constantly turn.
Yeah, it has to constantly turn. That's exactly right. So we have this really interesting thing that students will get confused about sometimes. Let's say my car is going at 20 miles per hour. Around the circle here. The car's velocity is going to always be tangent to that circle because it is moving in the same direction as the circle. You calculus students think tangent lines. So this is the first important thing, and that is that the velocity vector is always tangent to the circle. If that is the case, then what happens to the velocity vector as the car goes around the circle? Monica, how would you describe what's happening with the velocity vector as we go around the circle?
It's the same.
Same what? For example, I move, let's copy our car. This is definitely the wrong way, right? So I'm going to have to turn my car like so. And now if I were to draw my velocity vector, then I'm pretty sure that this, which is the same, is the wrong velocity vector. That's a crash right there. What do I have to do to this velocity vector to make it right? How would you make it right? Silly velocity vector. Yeah, I would have to change its direction. That's exactly right. My velocity vector now needs to point like this. And of course, probably means I need to redo my V. So the velocity vector is not the same. But what is the same about it? What did I not change? Yeah. Its magnitude did not change. That's the constant speed part. But its direction did change. So this is the weird part about uniform circular motion. The speed will never change, but there's always an acceleration. And that acceleration is changing the direction of the velocity vector without changing its length. Can you see that? So this is a new concept for us because moving in a straight line, we didn't have to worry about that. Yes?
So it was like directly across from it.
Mm-hmm.
It wouldn't have changed it would have been the complete acceleration.
Here?
Yeah,
And
but it had the same vector.
here. You can see that this is exactly wrong. So we need to flip. Oops, not that way. Smartboard's not being smart. Yes. It needs to be exactly opposite on opposite sides. Good visualization. Yep. Okay. So now the next question is, which direction and how much, what is the magnitude of our acceleration vector? That's all that we want to accomplish today. And so to do that, what I'm going to do is I'm going to allow the car to move a little bit. In fact, this is probably enough right here. And then, let me make this capital R for the sake of our formula here. And then we are going to pay attention to the average acceleration of the car as the car moves around like so. And then we're going to let delta t go to 0 to get the instantaneous acceleration. All right? Now, I'm going to check something really fast here to make sure that I'm keeping consistent with my plan. Ah, there we go. So actually, let's talk about just direction, and then tomorrow we'll talk about numbers, magnitude. So the question is, what direction does this acceleration need to be? And I claim I'm going to abbreviate uniform circular motion as UCM. And to get at this, I want to actually solve a more general problem, and that is, let's say I've got some object that's moving along a curve like this, moving in this direction, and here's my object, and he's obviously pointing in the wrong direction. He needs to be pointing more like that. And so his velocity vector is going to be tangent to the curve, just like so. And then as he moves along, this is V1, his velocity vector is going to turn and be just like that. And so if we consider the acceleration has to account for both a change in speed and also a change in direction. And I'm going to do a quick experiment here to show you how that comes about. So Josh, will you stand up and come this way? What I'm going to do is have you walk that way in just a moment. And I'm going to give you a couple of different pushes for a couple of different trials. And I want you guys to observe the effect. First thing, I'm going to have you walk that way, and I'm going to give you a push that way. Okay? Did I change his speed or his direction?
Speed.
His speed, because I was pushing the way he was going. And that would be true. Come at me. If I push opposite the direction that he's going, I change his speed also, right? So if we come back to our velocity vector right here, and I have an acceleration that is in the same direction or the opposite direction, then that causes a change in speed. We're going to call that a tangential acceleration because it points tangent to the curve together with the velocity. Tangential acceleration changes the speed of the object. And now we're going to go perpendicular to that and have a different acceleration, component of acceleration, back up here. Now this is going to be a little bit trickier to do, so let's get some space. And I'm going to have you walk this way, and I'm going to push you that way. So everybody see how I'm going to push him perpendicular to his velocity. Go. What did I just change?
His direction.
That's it.
That was fun.
And what I want you to observe about this is that right here where the direction is changing, that's where the path becomes curvy. Right? Anytime we have curve, that's because the direction is changing. And therefore, that requires a component of acceleration that is going to point perpendicular to the motion. And when it does, you can draw an imaginary circle right here that is tangent to the curve at that point. Right here. This tangent circle, the radius of that circle is called the radius of curvature, and I want you to notice that the circle that I've drawn, there we go, right at that point, that the acceleration that is causing a change in direction goes straight through the center of that circle. And so for that reason, we call this a center-seeking, or Latin, centripetal acceleration. And we're going to give that the symbol A sub C. And it changes the direction. And these two are always perpendicular to each other. Why? Because of the fact that you learned in geometry. What is true about the radius of a circle and the tangent? They're perpendicular. That's exactly right. So the tangential acceleration and the centripetal acceleration or center-seeking acceleration are always going to be perpendicular to each other. And these two together, the AC and the AT, are two components of the acceleration vector. So if I add them up, and I would add them by moving one of them head to tail with the other, like that. So there's my AC. Then when I add them up, what I get is the total acceleration in the vector sense. Notice that I can't add their magnitudes because they are vectors. In fact, because they are perpendicular, I would always add them using the Pythagorean theorem. So the magnitude of A in general is going to be the square root of AT squared plus AC squared. But we'll worry about that another day. What I want to worry about, and we only have 5 minutes to worry about it, is the direction that our acceleration vector is going to take and how we would figure out the path based upon it. So we're really just going to worry about sketching stuff. Well, let's take a look at our uniform circular motion, first of all, and figure out what we can figure out. In the uniform circular motion, we have constant speed, which means that our tangential acceleration must have what value? 0, because the tangential acceleration changes the speed, and the speed doesn't change. On the other hand, it's moving in a circle, so it is constantly changing direction, so it will have a centripetal acceleration. If this acceleration is centripetal, but not tangential, that means that the acceleration for uniform circular motion is always going to be pointing straight in towards the center. That's the characteristic that defines uniform circular motion. The acceleration is always pointing in straight towards the center. Yes, sir?
Can you correct that?
Sure can. Yes, ma'am.
So the centripetal acceleration points straight into the circle that is tangent to the velocity. Okay.
That's it. Yep. And in the case of uniform circular motion, that circle is the circle that the object is traveling on. Yep. So let's do some more sketching. Suppose I have an object that's moving along the curve. Let's do it like this. So my object is here, and it's moving along the curve. How would I draw the velocity vector? Yeah. Welcome. And how would I draw the acceleration vector? Well, that's a little trickier because I don't know if the object is speeding up or slowing down. But I can draw the centripetal portion of the acceleration. Which way is that centripetal going to point? Everybody draw that on your paper. Make a prediction. And you should have it pointing straight in towards the center. Not out, and not off of the direction, but perpendicular to the velocity, and straight in towards the curvature. Yeah.
For centripetal acceleration, will the acceleration vector always be pointing to the center of the circle?
Great question. The acceleration vector is going to be made up of the centripetal together with the tangential. And we don't know the tangential here. And the reason we don't know it is that we don't know if this object is speeding up or slowing down. or going at a constant speed. So let's come back and consider some possibilities. Suppose that my centripetal acceleration looks like this, and my tangential acceleration looks like this, and my velocity vector looks like this. This is one way that my object could travel. How would I draw the curve? Question number one. And what can I say about the speed of the particle? Well, the way that I would draw the curve is tangent to the velocity and curving towards AC. So I would draw my curve like this. Does that make sense? So we draw the curve tangent to the velocity, curving towards AC. And now I can assess whether the object is speeding up or slowing down by taking a look at the direction of the tangential acceleration. Notice that it is pointing opposite to the velocity vector. That means that something is pushing this the opposite of the way that it's already going. So what's it doing? It's slowing down. So this object is slowing down because AT is opposite the velocity. Take a different situation. Oh, and so now to complete this, Gianna, to answer your question, the total acceleration vector would be the sum of these two. So the total acceleration would point back just like this, over by AT and down by AC. Yes, sir.
So are the accelerations, are they kind of like forces that you add together, but they're not forces?
Well, they're forces divided by masses, really. Yep. Let me do another one very briefly, and then I'll turn you loose. If I have velocity and acceleration right here, notice this is the total acceleration vector. I would split it up into components. One component is perpendicular to the velocity, that's AC. The other component is parallel to the velocity, and that's AT. And now I can draw my curve. My curve is going to curve like that, tangent, curving around AC, and I would say the object is speeding up because AT is pointing in the same direction as the velocity. I know this was really fast. You can look at the last 5 minutes on YouTube.
So if there is no AT, it's going to constant speed.
Yes.
Is AT the same line as U? Is the tangential acceleration the same line as?
The same vector. It'll have a different magnitude.
Okay.
Yep.